Hi everyone. In this video, we're going to go through section 1.2, representing functions. Now first, we can take the word function or functions as a topic and let's break them up into two groups here, as I have here, called algebraic functions and then transcendental functions. All right, so algebraic functions are functions that contain terms that use algebra. So like when I say a power function, that innermost circle, something like f of x equals x squared. That's a power function. That's the first one. Polynomial, so we'll just string those powers together with plus or minus signs. So f of x equals x squared plus 3x plus 2 is an example of a polynomial function. That is a polynomial. Its degree is 2. And then rational functions, we'll just take those polynomials and put one over the other. So these are all using, addition, subtraction, multiplication, and division. That is an algebraic function. F of x equals, I'll take my x squared plus 3x plus 2 and put it over x minus 7. That's an example of a rational function. All right. Now, transcendental functions involve terms and expressions that transcend, go beyond algebra. So the first one, an example of a trigonometric function, a trig function, is f of x equals the sine of 3x minus 5. So there can be algebra in there, but the transcendental function comes into play when I have a sine term. Or an example of a logarithmic function is f of x equals the natural log of x minus 2. That's an example of a transcendental or of a logarithmic function. And then exponential functions, that's when our x is in the exponent. So even though that one looks really simple, that is called that is an example of a transcendental function because the x, the variable, is in the exponent. Okay, so these are all different things that we'll come across in the course, different types of functions that we'll come across in the course. And this section is just a brief review of them and then some of the terms that are involved. And we'll have the next section will be dive a little bit deeper into the review of some trigonometry. Excuse me. Now, the beginning of this section in OpenStax, it does go into a review of linear functions. So you should definitely read through that if you are not super familiar with linear functions and how we find the slope of a line and how we represent that. Then we talk about with power functions. When you have that f of x equals x to the nth power, most people are familiar with our little simple graph here of f of x equals x squared. We know that is a parabola that opens upward like that. I was supposed to touch the origin. I kind of missed. But we know that's a parabola that opens upward. And it is true that when n is even, when that exponent is even, the function values are non-negative, and the graph passes through the origin, opening upward. So if I were to graph f of x equals x to the 4th, x to the 8th, x to the 10th, x to the 12th, those functions all produce non-negative values. They hit the origin, and they all point upward. But as that exponent increases, the graph kind of gets tighter and tighter to the y-axis because the values become more extreme as the exponent increases. Then when n is odd, so an example of that, oops, I didn't write my squared there. Sorry about that. An example when n is odd, when my exponent is odd, right? When you cube an odd number, the answer stays negative. So my example for this one is going to be f of x equals x cubed. It does one of these guys, like that, right? The function has positive values when x is positive and negative when x is negative. X to the 5th, x to the 7th, x to the 9th, those will all look very similar to this, again, just being tighter to the y-axis. Right, so there's just being able to visualize functions and see what they look like as we go through this course. It will be helpful, right? And we'll, you'll graph some on your computer, and that'll help you to look at things. But understanding what the function, what the graph looks like, it will be helpful as we continue through this. When we have power functions, we know certain things about them based on what the exponent is. Similarly, when we have root functions, we kind of can visualize what they look like depending on what the exponent is, depending on what the denominator of the exponent is. So x to the 1 over n, remember, that's just the nth root of x, or really, to give a concrete example, right, we could have f of x is equal to the square root of x, right? When n is even, the square root, there is that implied 2 there. We don't write it down, but it's implied. When n is even, the domain and range are non-negative numbers, right? I can, the square root of a negative number is not a real number, right? It's that imaginary thing that you may have seen in some other, an imaginary number you may have seen in some other math course in the past. Okay, so if I want to represent what the graph looks like, right, the domain and range are non-negative numbers. So my square root function has a graph that looks like that. The square root of 4 is 2, so like that point there. The square root of 9, if I go like over here, is 3, right? This is obviously not drawn to scale. But that's what that graph looks like, right? When n is odd, however, right, that is defined. I can take the cube root of a negative number. The answer is, in fact, negative, okay? So to get an idea of what that looks like, right, interestingly, the one branch of a cube root or a fifth root or a seventh root function does in fact look like that. It would have a slightly different scale than the square root of x, right? But the other branch does that, right? This would be an example of f of x equals the cube root of x. No scales on there, right? The cube root of a positive number would be positive in this quadrant, and the cube root of a negative number would be negative in quadrant 3. Another type of function that we'll encounter is what's called a piecewise function. This is a function that has different definitions for different parts of its domain. All right, and when we use the term piecewise linear, that means all the pieces are linear. And if you look at this one here, right, what we'll see is we have 3 pieces to this function. There's this branch that has an open circle. That means it doesn't quite touch 2. There's a filled in circle here. That means that when we're at 2 on the x-axis, we're at 3 on the y-axis. And then the top branch, again, I have an open circle there, and then the graph does that. It goes downward, okay? And so what we're going to do in this example is we're going to take this piecewise function and figure out and write down how to represent the function algebraically, right? And what we see is we've got 2 lines there and 1 dot, all right? So what we'll do is I'm going to say, all right, f of x, it's g of x, excuse me. G of x equals, and then we make a squiggly bracket. Those are called braces, and a fairly wide one because I'm going to need to define this function with 3 pieces, okay? And what we notice in our domain is everything's happening at 2, right? If x is less than 2, then we have this first branch of our function. If x equals 2, then we have that point on our graph. And then if x is greater than 2, then we're at the top branch, right? And then maybe the easiest one to fill in is if x equals 2, right? Where am I when x equals 2? Well, I'm at the point 2, 3. So g of x is equal to 3. That's in the middle there. I don't have lines, but that's in the middle. G of x equals 3 if x equals 2. All right, now how about the left branch, right? This line here that I'm looking at, well, it's a line, y equals mx plus b. My y-intercept is 0, and my slope is up 1 over 1. So this is y equals 1x plus 0. That's the equation of that line, but I'm just going to write it in its simplest form, x. 1x plus 0 is x. All right, now we get to the next branch. Let's see. Our y-intercept. Well, I can't really see what the y-intercept is, so maybe I'll start with the slope. The slope, I go from this point, looks like I go down 1, and then to the right 1, 2. So my slope, I've got y equals negative 1/2, because I went down 1 over 2, x plus, I don't know what number, but how about I go up 1, back 1, 2. I'm right there at 5. So y equals negative 1/2 x plus 5. And that's this last branch of my function. Okay, so we can take, if we're given a piecewise function, we can draw the graph of that. Or if we're given a graph, we can step that backwards and figure out what the function is that produces the graph. Now we'll end this video, the last topic, talking about transformations of functions or shifting functions, vertically, horizontally scaling, and reflecting. All right, so what we're starting with in this example is y equals x squared, my black graph right here. And we're going to talk about how we produce each of the three other graphs in the picture, right? And the first one is the blue one. That is a vertical shift, right? The blue one is a vertical shift. You take y equals x squared. If I want to drop it down 4 units, well, you just subtract 4 from the answer, right? So the blue one is y equals x squared minus 4. That's it. That's how you shift that vertically. All right. You just add, subtract. If I add, that would shift it vertically upward. Subtract, shifting it vertically downward. Okay. Horizontal shifts are a little bit more involved. So the red graph looks just like the black graph, but it's 2 units to the right. Okay. The way that you make that kind of a transformation is I'm going to take y equals, throw it in parentheses. Right. I'm going to write x minus 2 and then squared. All right, so why is that, right? It's a shift to the right, but the minus 2 is in parentheses. The 2 is in parentheses, and it's the opposite sign, okay? A lot of students struggle to see why that is, right? But if you think about it, this point right here, the vertex of my parabola, right? To make the y coordinate 0, I have to have 2 minus 2 inside of the parentheses. That's the way that I like to think about it. To make the y coordinate 0, inside of that parentheses has to be 2 minus 2. Okay? Not the best explanation I've ever given, but we'll go with it. Just know that a horizontal shift, that goes inside of the parentheses, and it gets the opposite sign of the direction you're moving. So if I'm shifting to the left, that would be x plus 2 or 3 or 4. If I'm shifting to the right, it's x minus 2 or 3 or 4. Now the last graph on the picture is the green graph, and that has had 2 things done to it. It has been scaled, and it has been shifted vertically. Okay, I can see that vertical shift. It's down at -1. Its vertex is at -1. Okay, so in my equation, there is going to be a y equals, there is an x squared, and there is a -1. But it's not just x squared minus 1, because if you notice, this parabola seems a little bit wider than the other 3. Okay, so this one has also been scaled, and I know that it's been scaled by a factor of 1/4 because I looked at this problem ahead of time and figured it out. Okay, but the way that we can verify that it's been scaled by a factor of 1/4 is if we check check the 2 coordinate over there. If I take 2 squared, let me write it down. Oops, 1/4. 2 squared minus 1. Okay, 2 squared is 4. 1/4 of that is 1, minus 1 is 0. So if I check that point, it works. Like if at first maybe I thought that it was scaled by a factor of 1/2, right? Then that point wouldn't check. That wouldn't work out. But it's 1/4, and that does work. All right. So to scale, when we use fractions in front of the x squared term, that makes our parabola or our graph wider. Right? And if it were 2x squared or 4x squared or 8x squared, that would make the parabola narrower, tighter to the y-axis. All right, and then the last one, I don't have an example in the graph, but if I want to reflect my parabola over the x-axis, I would go like this. This you've probably seen in the high school course in the past. Let me put it over to the right here. Reflecting, if I graph y equals negative x squared, so the negative out in front, then that is going to take the black parabola and flip it vertically over the x-axis, or reflect it over the x-axis. That's my graph of y equals negative x squared. Okay, so that is just a brief overview of some of the functions that we will encounter and a little bit of information about them, right? We're going to go into greater detail as we move through the semester, but again, that familiarity with the things that you've seen in math classes of the past, if you don't remember them, it's not the end of the world, but the more familiar you are with them, the better your semester is going to go in terms of learning the new content. So take advantage of these review topics. Try to cram as much in your brains as possible, because it'll only be to your benefit in the end. All right, that is the end of this video. Thank you very much for listening. Have a wonderful day.